All right, we're going to review related rates or look at related rates. Related rates problems, the idea is to compute the rate of change of one quantity in terms of the rate of change of another quantity. One of these may be more easily measured, so we use the easier one, the one that you can measure, to maybe find one that would be very difficult to measure. And since we're dealing with rates of change, we've been looking at rates of change, probably some derivatives are going to be involved. There are some steps that we use to do this. We'll kind of work through those steps as we try one of these related rate problems. So this one says air is being pumped into a spherical balloon, maybe like someone's blowing a balloon up, so that its volume increases at a rate of 100 cubic centimeters per second. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? Okay, so things we want to do on these ones. Write an equation that shows the relationship between the variables. So what we got to figure out from this is, what are we trying to figure out here? And it looks like if we are putting air into a balloon and the balloon is increasing, we're talking here about the volume of this balloon. So what we have to know is what's the equation for the volume of a sphere, and that's one, usually they'll give it to you, or if you don't know, you should be able to look it up. 4 pi radius cubed is how we find volume of a sphere. Okay, so next thing what we want to do, write out all the other information from the problem. Any rates are written as derivatives of time. You may want to possibly draw a sketch if it would help you out too. When we do this, I like to put this like in a what we know category, and in some of the other steps we're going to figure out also what we need to show in order to do this problem. So other than this volume equation, what else do we know? We know that the volume increases at a rate of 100 cubic centimeters per second. That's a rate, and it's a rate of volume because we have cubic centimeters here. And so that's dV, change in volume, with respect to time. And so that would equal 100. And we'll throw units on there for now. All right, how fast is the radius of the balloon increasing? That's the question. That's over here in our show category. So what we want to find out is, how fast is the radius of the balloon increasing? That's a rate. So what we want to find out here is, what is d, the change in the radius, how fast, so that's a rate. How fast is the radius changing with respect to time? So we want to find dr dt. And the moment we want to find it at is when the diameter equals 50 centimeters. One thing you should check when you are doing these problems is your units matching up here? Looks like they are centimeters, centimeters. We're good to go there. Okay, so once you find your know and show, what we're going to do is differentiate with respect to time on both sides of our relating equation. You may have to use chain rule when doing that. So let's see if we can take our equation here, and let's see if we can differentiate it with respect to time here. So what is the derivative of the left side, v? That would be dv dt. That's our derivative there. On the other side, our only variable is the radius. So what we want to do is find the derivative with respect to that. So use our power rule here, bring down our 3. When we multiply that 3 to the 4/3, that's just going to make that 4. Pi is a constant, r, and then our radius goes down by, or exponent goes down by 1, so 2. But again, we're taking the derivative of something with r, so we need to include the derivative with respect to time there. Okay, so that was that step. Next step. Substitute all known values for variables and rates of change after we have done that differentiating. So this is where we want to now plug in something. Sometimes you may have to solve for needed values if you don't have a direct substitution. There's probably a way to find it out with some of the other information that's given. So what can we fill in here? Well, we know dv dt, we know that's 100. So let's substitute that in. 4 and pi are just constants. R, do we know what R is? Well, we don't have a measurement for R, but we do want to find out what this rate of change is when the diameter is 50. Even though it's not directly there, we should be able to figure out radius from that. If the diameter is 50, that means the radius is going to be half of that, 25. And so we do know the radius is 25. What we're trying to solve for here is drdt, because that's our show. So now if we solve that out, that should give us our drdt for our answer. And that's the last step, is to solve for the rate of change. Make sure you use correct units of measurement there. All right, so we know we're correct units of measurement. It's just solving this. Let's square that first. 25 times 25, or 25 squared, is going to be 625. I'm going to times that to 4, our other constant there. Now we got 2500 pi. And last step, to solve there, let's divide. So dr dt, our rate of change of our radius, is going to be 100 over 2500 pi. We can cancel out those zeros. So simplified exact answer will be 1 over 25 pi. With that, you should put measurements too. This is radius with respect to time. Our radius would be measured in the same thing our volume was, so centimeters in this problem per second. So that would be the exact solution. Sometimes on these tests, they do ask for the exact one. That would be the exact answer. If they want the approximate answer, then just divide that out. So if you do 1 divided by 25 times pi, the approximate answer there would be 0.0 like 127 centimeters per second. So if they want approximate, then you just round it off. Let's look at one more of those kind of basic ones. It says a ladder is 10 feet long and rests against a vertical wall. If the bottom of the ladder slides away from the wall at a rate of 1 foot per second, how fast is the top of the ladder sliding down the wall when the bottom is 6 feet from the wall? So what we got to figure out is what connects all this. What connects the wall, the ladder, the ground, the three things we're talking about? Well, it looks like it's forming a right triangle. What do we know connects the sides of a right triangle? This one's going to be Pythagorean theorem. So our connecting equation is Pythagorean theorem. We're going to be using a squared plus b squared equals c squared. Remember, when you're doing Pythagorean theorem, c always has to be that hypotenuse side. We'll call the up one a, we'll call the bottom one b there. All right, what else do we know then? The ladder is 10 feet long. So we can put that in our show. We know c here is 10. The bottom of the ladder slides away from the wall 1 feet per second. That's a rate. So what we got to look at is what's the bottom of the ladder. Here we're using b. So since that's b, that would be the change in b over time equals 1 foot per second here. And I'm going to put my units on that too. All right, how fast? All right, here's our question. How fast is the top of the ladder sliding down the wall? That's a rate. They want us to find dA dt there, because down the wall we got listed here as a. So we want to find dA dt when the bottom is 6 feet from the wall. So when the bottom is our b here, when b equals 6 feet. All right, so we got our know, we got our show. Let's go through and find our derivative. So on this one, doing derivative of each, use our power rule 2a. make sure we get our derivative in there with respect to time dA dt, plus the next one would be 2b dB dt equals, now the other side we got 2c dC dt. Okay, now let's substitute in what we know here. C is 10. We know that dB dt here is 1. We know we're trying to find this when b is 6. We're trying to find dA dt, so it's fine to leave dA dt in our problem here. The two things it looks like we're going to need to fill in here yet is what is dC dt and what is A. So we got to figure out what those two things are. Let's start with dC dt. dC dt is the change in the ladder. Well, is the ladder going to be changing at all during this problem? No. The ladder is going to remain 10 feet. So even though they don't tell us, something else we know is dC dt is 0. It's not changing. And so that we can put 0 in. A, what is A? Well, we should be able to find A, even though they didn't tell us from what we know here. If we're trying to find out the moment it's 6 feet, when we know this is 6 on the bottom, and we know the ladder remains 10, we should be able to find this A value at that moment using, again, Pythagorean Theorem. So if we got A squared plus 6 squared equals 10 squared, and solve that out, we can see that A ends up being 8. So at the moment that the bottom is 6, the side is 8. So now we plug that in, and we can now solve this out for our. All right, so keep going here. We got 16 dA dt plus 12 equals, all that is going to be 0. Do a little subtraction and dividing here, and we should be able to find our rate. So the rate of change of this going down the wall would be negative 12 over 16, or 4 goes into both of those, so negative 3/4. And make sure you get units on there. Here we were working and everything was in feet and per second. In this case, the negative, what that indicates is that this is moving downward. So usually in these problems, up is positive, down is negative, right is positive, left is negative. So that just indicates the direction. The speed is 3/4 of a foot per second.